Newton's method, also known as Newton-Raphson, is a very popular numerical scheme for finding a solution to the equation f of x equals 0. And we're going to take a look at how exactly this works. So the requirement for this method to actually work is that the function f of x has to be continuous and differentiable. But once it is, we can actually do quite a lot in terms of finding the root. So let's do a plot. I'm trying to do nicer plots for once. Okay, so here's the idea. Let's suppose that we have a function that goes something like this. So it goes whoop, like this. So this is f of x. And somewhere down here is the root that we're trying to find out. However, let's suppose that our initial guess isn't so well educated. Let's suppose that we're actually quite far away. We're sort of up here. So our initial guess is x0. So here is the idea of Newton's algorithm. Basically, what you do is, first of all, you compute the function at the initial guess. So the y-coordinate of this particular point would be f of x0. And then what you do is you plot a tangent. So you consider a line that's tangential to the graph. It could go something like this, for example. And you consider this tangent and you consider where it intersects the actual x-axis. And that's going to be your second guess. So your second guess, which is x1, is going to be here. And once again, you compute the value of the function at f of x1 now, and you perform roughly the same thing. So once again, you do a tangent, you end up at a point x2, and eventually, sooner or later, you're going to end up at a point which is either at the root or very close to the root. So you might have some guess x3, for example. And this is pretty much the gist of Newton's method. So essentially, if we were to formulate this symbolically, we would say that the iteration xi plus 1 is actually computed based on xi minus the value of the function at xi divided by the first derivative, once again at xi. I'm sure you can see where the first derivative comes from. The tangent to the line happens to be the first derivative. So this is essentially an iteration formula because the solution is found by repeated application of this equation for each subsequent value of I. So let's take a look at a very simple example. So let's suppose that we're trying to solve the equation 1 over 2x minus 1 equals 0. Now we know we can solve this analytically. We know that x is actually equal to 1/2, but let's suppose that we want to try and find this numerically. So once again, if we do a quick plot of the function, let's do a quick plot. So essentially it's going to go something like this, and essentially that's our f of x here. So we're going to start with, once again, an initial guess. And this time, if let's say this is a 0.1 and this is a 0.2, we're going to start with some guess, which is, let's say, 0.2. So we say initial guess is 0.2. And then for a numerical solution, for the solution using Newton-Raphson, remember we need the first derivative as well. So we need to take this function 1 over 2x minus 1 and we need to differentiate it. So the first derivative of this function happens to be minus 1 over 2x squared. Okay, so we now have all the parts we need to apply Newton's method. So essentially we can formulate the expression for x at n, or let's do I, x at I plus 1. And we're going to formulate it as xi minus f of xi divided by f prime of xi. That's Newton's method. And now we perform the substitution. So essentially for the function, so we have xi minus, and then the function of xi, that's this whole thing essentially. So that would be 1 over 2xi minus 1 as the numerator, and then the denominator is the first derivative, so that would be minus 1 over 2x squared. And after we simplify this a little bit, we get xi plus 2xi squared multiplied by 1 over 2xi minus 1. And just factoring out the xi, we can say that this is essentially 2 times xi minus xi squared. Okay, so we now have an expression, an iterative expression for the subsequent term, and what we can do is we can actually start plugging in these values. So first of all, we're going to plug in our initial guess, which is 0.2. So we're going to say that x1 is equal to 2 times, and then here is what we need to plug in. So that's going to be 0.2 minus 0.2 squared, and that's going to be about 0.32. Now our subsequent guess, x2, is going to be 2 times this guess, 0.32, minus 0.32 squared, which is equal to 0.4352. And then let's do another guess, x3, and this guess is going to be 2 times 0.4352 minus 0.4352 squared, and that's going to be roughly 0.4916, which is very close to the actual value of 1/2 that we know is the actual answer. So here it is. In just 3 iterations, we managed to get to within 1/100th of the actual value, and that's fairly quick, and that's why the Newton's method is actually so popular. Alright, let's take a look at the Newton-Raphson implementation in MATLAB. Now it's actually very simple because all I have here is a function which takes some function f and its first derivative, and it applies the Newton's method for the number of iterations that we specify with the initial guess that we specify. So let's actually try feeding it some data. So first of all, we're going to have the function itself, and that's going to be 1 over 2 times x minus 1, just like we had in the example we just did. And we're also going to have g defined as a function of x, which is going to be that first derivative. So that was minus 1 divided by 2 times x squared, like so. So that's g. And now what we can do is we can call simple Newton's method, and we can call it with f, g. We're going to specify an initial guess of 0.2 as well as 3 iterations. And here is what we get, 0.4916, just like we had in the example. And we can certainly increase the number of guesses. If I increase it to 10, for example, you're going to see that we get a perfect 0.5.